Towards a Principle of Least Surprise for Bidirectional Transformations. I'm Perdita Stevens, and this is joint work with James Cheney and James McKinna from Edinburgh and with Jeremy Gibbons from Oxford. I'm going to talk from the same slides that I used at the BX workshop 2015 last week in L'Aquila, but I'm going to do so rather more slowly and with less energy. Perhaps this will still be somewhat easier than reading the paper, however. So the very first thing I should say is that actually the paper is quite diffuse, covers a lot of things, and I'm not going to talk about all of them in this talk. So if you like this talk, please read the paper. You'll find more stuff that you like in there. And if you don't like this talk because you think I've left out some very important things, please read the paper, and perhaps I've covered them in the paper. The overall plan is that first of all, I'm going to try to motivate why we need a principle of least surprise. And then I'm going to go on and look at what is in some ways the most obvious way to try to build such a principle. And this will be a principle of least change via metrics. When we came in, we were certainly thinking about a principle of least change, and that's the title of the grant that funded this work. But the more we thought about it, the more we realized that what we actually wanted was a principle of least surprise. So I'm going to try to explain why that's the case, and then go on to consider what a principle of least surprise might look like. And finally, I'll list some of the areas that we haven't even touched on in this talk. So I often liken a talk to start off by telling people things that they already know, so let me do that here. A model is an abstract, usually graphical, representation of some aspect of a system. And I'm using the term system here very broadly to include the requirements and the outside world and perhaps even the humans. So model is an extremely inclusive term. Don't necessarily think UML model. Model-driven development, MDD, is software development in which models are important, and we'll principally think about software development that involves model transformations, etc. Need not necessarily be. Why are we interested in model-driven development in the first place? Well, one of the fundamental problems with software engineering is information overload. Our requirement for ever more complex software has long since outstripped the ability of limited human brains to contain all the different concerns and details that arise in such software development. So model-driven development, by being development in which there are various different models, each adapted to the needs and concerns of an individual expert or expert team, enables the people who have to take decisions about a particular concern to use a model that reflects all and only the information that's relevant to them, and to take decisions in that context without being overloaded by a lot of information and changes in that information that they didn't need to know about. In other words, the key motivation and raison d'etre for MDD is managing information overload. And by that we mean avoiding distracting the expert with information that isn't relevant to them. So in an ideal world, the model that's being used by a particular group of experts would contain all and only the information that's relevant to them. And the only reason their model would ever change would be because of things they need to know anyway. So perhaps it changes because they changed it, they made a new decision that's within their remit of concern. Or maybe it changed because of something somebody else did, but that change was caused by something that they had to know about anyway. And so there's no extra surprise in that change. They understand where that change came from. Unfortunately, the world is not ideal, and one can argue that this is why software development is hard, that you can't perfectly separate concerns, that things are always intertwined, that we really require human intelligence, and we would really like a lot more human intelligence than we can provide with humans. In other words, in some ways, least surprise is the whole point of MDD. Or to put it another way, surprising the experts using the models is one of the things that can scupper MDD. So we'd really better get it right. We want to try to get as close to that ideal world as we possibly can. Now, of course, people have talked about least change for a long time in bidirectional transformations. Here is Merton's original formulation of the idea. The action taken by the maintainer of a constraint after a violation should change no more than is needed to restore the constraint. When you start trying to formalize that, you realize that there are some devils in details. But at least there's an extreme case which is easy to formalize, and usually it's easier to agree on, although not absolutely always. And that is Hippocraticness. If nothing needs to be changed, in other words, if your models are already consistent, change nothing when asked to restore consistency. Nothing needs to be done. One of the things we might bear in mind when we think about this subject is the idea of having a meeting of developers whose native models are different, where the purpose of the meeting is simply to restore consistency between their models. The idea is that what we would like to formalize and ultimately implement in a tool is the decisions that such a meeting would reasonably take. And so this extreme case is to say, if you have this meeting between the developers using model A and the developers using model B, and they say, what do we need to do to restore consistency between our models? And they say, oh, our models are already consistent. Then the answer is, you don't have to do anything at all. The meeting is over. You can talk about something else. So let's start off by taking a naive approach and see how far we get. So let x be how much we need to change to restore the constraint, and let y be how much the Bx actually changes. Well, according to Merton's formulation, we ought to ensure that y is less than or equal to x. Y is no greater than x. Well, y had better not be any strictly less than x, because if the amount the Bx actually changes is strictly less than the amount needed to restore the constraint, well, then it didn't restore the constraint, did it? And its job is to restore the constraint, restore consistency. So what we're actually saying is that the Bx should change exactly the least that's necessary to restore the constraint. This is all very well, only how do we measure those two amounts? Fortunately, mathematicians know how to measure things, and the simplest and best known way to do this, that you probably remember from your undergraduate maths courses, is to use a metric. So given a space, M might just be a set of models, a metric on it is a function which takes two elements of that space and gives you back a real number. And in order to behave sensibly as a way to measure distances, it needs to satisfy these three axioms. First of all, it must be the case that the distance between two things is zero if they're the same, and only if they're the same. You can't have zero distance between two different things in a metric. The way of measuring distance doesn't depend on which direction you go along the path from one thing to the other. It's symmetric. And the final rule is the triangle inequality. You can't make a shorter distance from M to M double prime by going via some intermediate point M primed. You can almost certainly make a longer distance between those things, and we have in L'Aquila many examples of that in the train network, but at any rate, going via some place shouldn't make your distance any shorter. And one very easy example of a metric usually is minimal edit distance. Now this is a rather special metric because it has as its codomain not real numbers in general, but rather natural numbers that count something like how many mouse clicks or key presses do you need at a minimum to get from one model to another model. I'm saying typically there because minimal edit distance wouldn't necessarily satisfy all the metric axioms. The one that's most likely to fail is symmetry, because in some cases you might have an edit that can take you from M to M primed that's, say, via a complex refactoring, where there's no refactoring that would take you in the other direction. But that's a corner case. So suppose we're given a Bx given by its consistency relation R and its forward and backward consistency restorers, R forward and R backward, between spaces M and N. And this is a good place to say, in this talk, I'm really only going to consider these purely state-based relational Bx. In the paper, I talk a little bit more about books that use a more complex setting that might involve deltas or whatever. But for simplicity, I'm only going to talk about the simplest case here. And suppose we're also given some metrics, which I'm going to call d sub m and d sub n, on those model spaces m and n. So in both m and in n, I can measure distances between models. But there's not necessarily any relationship between the way in which I measure distances between in those two places. Now I can say that our Bx R has the property of being metric least if it is the case that, it makes sense to read this constraint from right to left, in fact, the distance in n between the model in n where we started and the place that our forward consistency restorer R forward takes us when we ask it to restore consistency between m and n is less than or equal to the distance between where we started, n, and any n primed that is consistent with m. In other words, the forward consistency restorer does the best it could possibly do. It takes us to some new model in n, which is notated R forward mn, and that model is at least no further away from n than any other place that the Bx could have taken us to and still been correct. And of course dually. Well, that's an interesting and obviously reasonable place to start thinking about metric least change. And Macedo and Cunha implemented this approach, and the way to think about what they did is that they provided a new semantics to the syntax of the OMG standard bidirectional model transformation language QVTR. So in their setting, your Bx writer would still use the QVTR syntax to express a Bx, but what they wrote would only consult the OMG semantics in as far as it explained what the consistency relation embodied in that Bx is. The OMG semantics for consistency restoration would be completely ignored and replaced by this new way of saying, how does this Bx actually restore consistency? So we're given a consistency relation R by being given a text in QVTR, and we're given models m and n, and our task is to find a new n primed that is consistent with m. So what do? We first of all set our candidate distance d to be 0, and then with our current candidate distance we search exhaustively for models n primed that are consistent with m and are at a distance d from n. So at our very first step we look at this and we say, is the only model which is at distance 0 from n, namely n itself, already consistent with m or not? Later on we may be looking for all models n primed at a distance 3 from n or whatever. If at our current candidate distance d we find one or more consistent models, then we present them all to the user as options. As far as least change is concerned, they're equally good. Their tool presents those to the user and asks the user which consistency restoration that's at this minimal distance they would like to have. If we didn't find any consistent models at distance d, then we had better increment d and go back to step 2, because we have to be content with a larger edit distance between where we are and where we want to be in order to restore consistency. There are a number of problems with this, as indeed explained in Macedo and Cunha's paper. One is scalability. The initial tool that they implemented was of course a research prototype and didn't really work with non-trivial examples. We might ask ourselves whether with a clever implementation or clever solutions to the technical problems here we might come up with a more scalable solution. We think probably not. We think that the results of Bunneman, Kanner and Tan relating to a similar situation in databases and demonstrating NP hardness of even very basic simple problems in their PODS-02 paper is very strongly suggestive that we'll never find a reasonably scalable solution that will enable us to build a usable tool with this metric least change approach, and so that's unfortunate. Usability is a problem that might be soluble with some clever design work in the language. It's not really very satisfactory to give all the models at a given distance to the user and ask them to select the closest model. That's not something that users are going to be very happy with in practice. But there's no easy way to ensure that there is a unique closest model, and on the face of it, it's not obvious how to allow the Bx programmer to specify the choice. There are various things you could do. You could invent mechanisms to allow the Bx programmer to specify how to break ties where appropriate, or as I believe there's some ongoing work doing, you could use some clever heuristics to try to present the candidates to the user in a good order, such that the one they're likely to want is usually the first in the list, and that will reduce the burden on them somewhat. But that's a problem that would have to be solved somehow. Metric least change Bx don't compose even where that makes sense, and I'll come back to that point in case you don't believe me. Where does it make sense? Well, we certainly know how to compose asymmetric lenses, and asymmetric lenses are a special kind of these set-based relational books, so we can certainly compose those, and then it makes sense to say, if you have two of those asymmetric lenses and they both are least change in this sense, then is their composition least change? And unfortunately the answer is no, for a rather fundamental reason. The intuition to have here is to say that metric least change says, never mind if what you can do is absolutely terrible, just do your best. Now, then the composition is essentially saying, you must go via this middle point, and at each leg, do the best you can, even if that's absolutely terrible. Now, the composition of two best you can, but possibly absolutely terrible things isn't necessarily the best you can do if you remove the constraint that you have to go through the middle thing. It's essentially a version of not all triangles being degenerate. And the final point that I'm going to talk about in a moment is inflexibility, because metric least change gives you this strong constraint deliberately on what a right answer should be. It should be a model such that there is no model any closer to where you started that is consistent. If the Bx programmer says, but I know what I want to be the answer to restoring consistency here, and it actually is a thing which isn't quite the closest, but it's better in other ways, then they're out of luck. That's just tough. That Bx can't be least change in this sense. Now, to some extent, we can mitigate that inflexibility by allowing the Bx programmer to choose the metrics on the model space, but that's not entirely satisfactory, because the kind of intuition one wants to have is that the user knows how far apart they think models are. They certainly know whether they think M1 or M2 is closer to M, and then if you try to invent a Bx that's specific to, you try to invent a metric that's specific to one Bx, that's a bit cart before horse-ish somehow. So let me give an example where this inflexibility bites. Suppose the model space M is the collection of UML models, and the model space N is a collection of test suites in JUnit, say. And the consistency relation we're going to have is to say that a UML model M is consistent with a test suite N. I see I'm missing an S in the definition of N, by the way. If and only if every class in the model M which is stereotype persistent has a test class of the same name in the test suite N, and that test class contains an appropriate set of tests for each public operation, and the ... there indicates that we ought to specify more precisely what that means, but it's going to mean that for each public operation there should be at least one JUnit test that tests the public operation, and perhaps we want to put some constraints on that if it takes a Boolean, there should be a test that has the Boolean input being true and one that should be false, and whatever, reasonable kind of coverage sort of condition. Okay. So now suppose that you take the test class for some persistent class in the model and you modify it. Perhaps you modify it in response to something the people who are thinking about implementing this stuff tell you. And let's say, for example, that you change the type int to the type long throughout your test class, because people have decided that's the type they want to be using. Now you restore consistency, and you, in effect, propagate that change back to the UML model. You say, I want the UML model changed so as to be consistent with this now modified test class. What should happen? Well, what you probably want is that in the UML model, the type int, wherever it appears in the specification of public operations in the class, should be replaced by long throughout. You want, in fact, the same change to take place in the model as in the test suite. Unfortunately, however, there is a smaller change that restores consistency according to our consistency definition and is almost certainly not what you want. We could just remove the persistent stereotype from that class in M, because according to our consistency specification, if there is no persistent stereotype on the class, then there are no requirements for consistency concerning that class, and so that restores consistency. Oops. So what could we do about that? Well, we could use a different metric. So we could say, well, we had better make removing the persistent stereotype an enormously expensive change, so that, even if we have to replace int by long in 20 different places in this class, it's still going to be cheaper to do that than to remove the persistent stereotype. But unfortunately, that probably doesn't accord with how the user thinks about distance in their model space, and so essentially what we've done is we've defined a metric specifically to cause this Bx to have the behavior we wanted to have, and that's not terribly satisfactory. The other thing we could do is we could dig into why we feel that removing persistent is not the right answer. Why is it not as cheap as it looks? We could argue it looks as though it's cheaper than it is, because when we are saying it's a small change, we're saying it's a small change to the model, but actually it's a very important change to something else. It's a very important change to the connection between the two models. If you think about saying, well, really, there's a link between a public operation foo represented in the class within the model and the JUnit test of operation foo in the test suite, every one of those connections gets disrupted, gets broken when we remove the persistent stereotype, because we now say, oh, actually that class wasn't persistent, it's got nothing to do with any test class in the test suite, and so all those links are broken between all those operations and all those tests. So we could argue removing the persistent stereotype is a small change to the model, but it's a large change to the witness structure that explains the consistency between the model and the test suite. Let me spend a few moments talking about witness structures. What we mean by a witness structure is any structure whose intention is to capture something about the relationship between the models being kept consistent. And this is something that turns up a lot in books and in many different guises. So here are some examples. In our straightforward set-based relational books, we really have no further information about why items in the two model spaces are consistent. We just say they are, that pair of models is in the relation. And that's equivalent to saying, if you like, they're consistent because I say so. In TGGs, we may say that the witness structure is the derivation tree of the correspondence graph. We may want to say they're consistent because this is how they're built up together using the TGG rules. In certain kinds of model-driven development with trace links around, we might want to say they're consistent because this part of this model links to that part of that model, and so on for all our different trace links. I did some work a while ago capturing the semantics of QBTR via a particular game between verifier who wants to show that two models are consistent and refuter who wants to demonstrate an inconsistency between them. And in that setting, we may say these models are consistent because here's how verifier wins a consistency game on them. Here is a winning strategy. We might even, of course, say they're consistent because here is a proof that they're consistent. It may perhaps even here is a proof that our theorem prover gave us that they're consistent. And so all of these things are auxiliary structures beyond the models themselves, such that we might care how much they change. So we might perhaps get some mileage out of least change in this naive metric-based sense by saying what the property we really want out of our books is that they should minimize the amount of change to the model being changed together with the witness structure, which is also being changed when we change the model. That could probably repay some further research. So metric least change may be useful in some settings, or where its deficiencies can be mitigated. But I hope I've convinced you that it has enough drawbacks that it doesn't deserve to be seen as the sole right answer. We shouldn't just go home and say we've done it. So let's go back to the drawing board and think about some alternatives. So to do this, let's go off to user interface design, where principle of least surprise is often talked about, and you will often teach people who are learning to do interface design about a principle of least surprise, sometimes known as a principle of least astonishment, as a way to think about how they should define their interfaces. And that idea gets adapted to language design, and we can now adapt it to books. There doesn't seem to be a single agreed formulation of a principle of least surprise, but here is the one I found in Wikipedia, which comes from a book by those people, Salzer and Kashuk. It says, people are part of the system. The design should match the user's experience, expectations, and mental models. Now, the interesting thing about people's mental models is that they often find it easier to explain when their mental models have been violated than they find it to explain what their mental models actually are. And in fact, while I was preparing these slides, I overheard a conversation between my husband Julian and my son Robin, in which Robin was looking over Julian's shoulder and Julian was doing something with some annoying computer system. And Julian said, "That's not what I expected." And Robin said, "What did you expect?" And Julian said, "I don't know, but not that." And I think that's very characteristic. That kind of thing happens a lot. So the point about the principle of least surprise is not that the user should always know exactly what will happen, exactly what will be on the next screen. The point is rather that they should seldom be surprised. They should seldom be taken aback what happens. And if we look at that a bit, what we see is that we're not, even though we have least in the name of this surprise, there isn't really any least about it. This is not about optimal behavior. It's about reasonable behavior. Perhaps the leastness is the least occasions on which we see unreasonable behavior, or something like that. So you have to put up with my hand-drawn cartoons at this point, because a while ago I got into trouble with I got my department into trouble by using a picture which had told me on the site I downloaded it from that it was public domain, and turned out not to be public domain according to the photographer who'd taken the photograph. So from now on, I draw my own pictures, however badly. And you also have to insert your own minion joke, because until my co-authors told me when I showed them these slides, I didn't know there was a thing called minions that I ought to have known about. So there you go, never mind. Anyway, boss and minion each have a model, and they are each working on their own model, and from time to time they have to synchronize. And so in this slide, boss is telling minion to be fine and go away and modify his own model, but to keep him informed so that he can from time to time update his model. He doesn't want any nasty surprises. Okay, and minion, whose job depends on it, is going to do his very best to ensure that he obeys that instruction. So now he has to go away and scratch his head a bit and say, how can I be sure not to violate boss's expectations here? I have to change my model, he says, but I mustn't give boss too much change. Boss doesn't want any nasty surprises. How much change can boss take? Maybe boss can cope with his model changing by an amount epsilon as a result of the changes that I make to my model. So I'd better make sure I inform boss before I do something that's going to cause his model to change by more than epsilon. How can I do that in terms of what I can see? In other words, in terms of how much I change my model. Maybe it should be enough if I make sure I inform him before I've changed my model by any more than an amount delta. Now, my use of epsilon and delta in there should be setting off memories of your Analysis 1 course at university, probably, where you probably met the idea of a continuous function. So here's our standard mathematical definition of a continuous function from S to T, each equipped with a metric ds and dt. We say a function is continuous at a given source point, little s, if, however close we want to get to the image of our source point, we can get that close by making sure that we stay close enough to the source point. That's one informal way of reading what we've got here. We're going to say, for any epsilon, we can find a delta such that every point that is within delta of our source point has an image which is within epsilon of the image of our source point. and we just say that the function is continuous if it's continuous at all source points. And this is a reasonable measure of, reasonable behavior of a function. We're used to the idea that the most reasonable functions are the continuous ones. There are lots of variants, so I'll come to that in a moment. How do we adapt that to books? Well, in the case of books, the points we're concerned with are really pairs of models. So let's suppose we have a pair of models, Mn, and we'll say that the forward consistency function is continuous at our pair of models Mn, and you might think of M as being the minions model and N as being the bosses model in this case. If it's the case that, provided the size of the change we make from M to M primed is less than delta, it will follow that the amount of difference it makes, whether we restore consistency forward with respect to N at M or at M primed, is less than epsilon. So you have to think about that a moment. What we're really saying is, suppose that the users of our model space M are not sure whether to make this change of size delta. Provided it's a small enough change, their decision about that should only make a small change in the model N. So we're not saying anything about the distance between N and R forward of Mn or R forward of M primed N, because we're not guaranteeing that M and N were consistent to start with. So M and N could be wildly inconsistent, and it could be that the distance between N and anything which is going to be consistent with either M or M prime has to be enormous for that reason. But at least the choice between M and M primed should not make a big difference on the N side. Now this is nothing other, in fact, than saying that the one argument function from M to N that we get by plugging in the model N as a constant is continuous at source point M. So at which points Mn do we want continuity? Well, we might want to say we want continuity everywhere, and in the paper I call this strong continuity. Or we might want to say that we only want it if we actually start at a consistent pair, and in that case we have weak continuity. And if we're in that situation, then of course that top point R forward, Mn, is actually going to be equal to N by Hippocraticness. If they're already consistent, then R forward is just going to return N, and in that case we get a rather simpler picture, in which case we say, provided we have a change less than delta on that side, we get a change less than epsilon on that side from N. But if we might have to allow the models to be edited concurrently, then we can't necessarily guarantee that we start from a consistent point. So it is, I think, interesting to consider both options. We might also want to think about something other than everywhere or only at consistent Mn. We might be interested in starting with the given books and asking where we get continuity, in the sense that those are the points where the books is well behaved. We might be particularly interested in a guarantee of continuity that applies at all points that are in a good subspace pair. I'll have a picture of that in a moment. Worth noting that in the history ignorant or very well behaved or put case, the distinction between strong continuity and weak continuity goes away. There's a one-line proof of that in the paper. Now, a really nice thing about this notion is that strongly continuous books compose where composition makes sense, and also weakly continuous books compose where composition makes sense. And I'm sure if I knew enough category theory, I would be able to say, that's because this. But actually what I did is to write out an epsilon delta argument that shows that, and it's just like, exercises you probably did in your undergraduate analysis course. It's very straightforward. Let's talk a moment about subspace pairs. You may remember that a subspace pair within a pair of model spaces that are related by books is a pair of subsets of the model spaces. So we might want to say that this pair of a green space here and a green space here forms a subspace pair within the whole model space here and the whole model space here. And it forms a subspace pair if the experts who are using the two model spaces can jointly agree to stay within the subspace pair. So in other words, it's a subspace pair if the books has the property that, provided the user doesn't move their model outside the green, the books will never do so when it restores consistency. So if you apply the books' consistency restoration functions to a pair of models that involves a model in the green here and a model in the green here, then the model returned by the books will always be within the green. So in saying that we might want continuity on that subspace pair, what we would be saying is, well, you already knew that those green spaces were good in the sense that you could guarantee to stay there, provided that, developers on both the model spaces agreed that they weren't going to go outside them. But also, if you stay there, you're going to get nice continuous behavior. And one of the things we might want is we might want a books tool that goes beep when you move outside a known good subspace pair like that. It might be that sometimes you can't guarantee always to stay in this space, but you might like the tool to let you know that you are now in danger of having surprising behavior when you restore consistency. And I think that's also worth further thought. Of course, it couldn't be as simple as to say that continuity is just the answer. There's one major problem with continuity as a measure for books in MDD, and unfortunately that is that every function is continuous at an isolated point. Now, what I mean by an isolated point is a point such that there exists some capital delta, say, such that there is no... So M is an isolated point if there exists some capital delta such that there is no model not equal to M that is at a distance less than capital delta of M. And unfortunately, in our very discrete model spaces that we typically work with in MDD, every point is an isolated point. So that unfortunately means that continuity is not going to be a very interesting property of books' restoration functions. Fortunately, in analysis, many variants of continuity have been considered, and we might well find ourselves a variant that has better overall behavior, and several of them are considered in the paper. The one that we think might be promising is holder continuity. That we think is going to be way too strong to expect it to hold everywhere in realistic books other than in very special circumstances. But we do think that identifying subspace pairs on which a books is holder continuous might be worthwhile because of the possibility of saying, okay, that's a nice safe space where you probably don't need to inspect the books' behavior too closely, you can just trust it. But if you get outside that subspace pair, the tool might go beep and you might need to invest some more effort in testing or inspecting what the books does. So that's about all I want to say. Here are some of the areas that we perhaps should have considered in more depth in this talk and really haven't. We talk about some of them a little bit in the paper, so you might want to have a look. Other ones rather not so. So there is a section in the paper about category theory, but I haven't talked about it at all today. Given that we know a bit about how to think about least surprise with category theory, and we know a bit about how to think about least surprise with metrics, an obvious question is, well, what about topology? Can we make some headway there? It would be very interesting in particular to think about algebraic topology. And if only I remembered more about my algebraic topology course as an undergraduate, I might have something more interesting to say about that, but right now I don't. A related issue is to think about various different kinds of type theory. We have some ongoing work involving dependent type theory, in particular relating to witness structures, which I mentioned on the way through. It would be lovely to make a connection with homotopic type theory as well, homotopy type theory. I talked a little bit about subspaces, but there's probably a lot more to be said there. I haven't really explored yet what the relationship between these ideas and the ideas that I wrote about a year or two ago about partial books, so books which might not fully succeed in restoring consistency, but might do something like only making the uncontroversial changes and leaving the cases where some intelligence was required to humans. We might wonder about heuristics. As mathematicians, we prefer to stay away from heuristics usually, but it might well be that the heuristic approach leads to good usable tools in the end. We don't know. Can we combine heuristics with some checking of what they actually achieve? Don't know. Some kind of ideas from Lagrangian Hamiltonian mechanics or from simulated annealing, perhaps in that kind of direction, might be worth looking at. And that's all I have to say, unless you would like to see an example of why the metric least change approach doesn't compose. Suppose we have our three model spaces M, P, and N like this. And now we're going to say they're related by two ordinary set-based relational books, R and S, R relating M and P, and S relating P and N. And suppose the models within these spaces are like this, and the way I want you to think about it is that the metrics are the ordinary natural Euclidean distance in the space, so M1 is closer to M than M2 is. And consistency, I just didn't get round to drawing a nice picture to show this, but M is supposed to be consistent with P, P is supposed to be consistent with N, and M1 and M2 are both supposed to be consistent with both P1 and P2. P1 and P2 are both supposed to... no, sorry, that's not what I want. M1 is supposed to be consistent with P1, M2 is supposed to be consistent with P2. And both P1 and P2 are supposed to be consistent with N primed. And that's all. Okay. Now, R is an isomorphism, a bijection. Okay, so there's going to be no choice there. S is a real abstraction. We're actually abstracting P1 and P2 both onto N primed. Okay. So our forwards consistency relation, it's just going to be get, if you're happy with asymmetric lenses, has no choice at all. Okay, this is what it has to do. It has to implement the bijection at the R level, and it has to implement the abstraction at the S level. Okay. And of course, for composition, we just compose like that, and we know how to compose consistency relations. We just compose them the same way we always compose relations. The interesting case is the put function, the backwards consistency restoration. So how do we produce a new element of M that should be consistent with a given N primed, starting from an old model M here? Well, we know how to do this. These are lenses. First of all, we bring M forward to P using the get function, the forward consistency relation, forward consistency function. And now we apply the backward consistency of S to take P and N primed to P1. Okay. Now, it did have a choice. It could have given us P2, which was also consistent with N primed, but because, let's say, it's trying to be a metric least books, it's going to give us P1 because that's the closest model to P that is consistent with N primed. Okay, so if it's going to be metric least, it has no choice. It must do that. Okay. And now we remember that we have a model M over here, and we use the backward consistency restoration of R to give us our final answer in M. And in this case, R, which had no choice at the backward consistency restoration because this was a bijective books, is going to give us M1 as the answer. And indeed, we're happy about that because M1 is indeed the closest model in M to M, which is consistent with N primed, which was the model we were supposed to be consistent with over there. So in that case, it gave us the right answer. We had two metric least asymmetric lenses, okay, special case of set-based relational books, and composing them gave us a books which is also metric least, so we were happy. However, now suppose that we change the metric on the middle space P. So I've illustrated that just by swapping the positions of P1 and P2 in how far away they are from P. So everything about the consistency relation stays the same, but now in P, P2 is closer to P than P1 is. And again, we're going to restore consistency backwards between M and N primed. We're going to construct a model M here, which is going to be consistent with N primed. So we do the same thing again. We bring M forward to P, and now we have to restore consistency backwards using S between P and N primed. But this time, if S is a metric least books, it's going to have to give us P2, because that's the closest to P that's consistent with N primed. So now, when we restore consistency with R between M and P2, remembering that the backward consistency restoration of R has no choice because R was a bijection, has a bijective consistency relation, it's going to have to give us M2 because there's no choice. But actually, as far as the composed books goes, that's the wrong answer now, because what we really wanted to do, we wanted the composed books to give us M1 just like it did before, because as far as M and N are concerned, nothing changed. So unfortunately there we have the composition of two metric least books whose composition is not metric least. So that's what I mean when I say that the metric approach doesn't compose. And I will stop there. Thank you for your attention.